Okay, P14 next. This is the particle model, so huge links to your chemistry. I will definitely be teaching this before you do the mock, but I'm making this available nice and early so you can sort of do some sort of advanced learning should you wish. So the first part, piece of metal's got a mass of 6.4 grams. It wants it in grams per centimetres cubed, so I'm happy with that. The density of the, sorry, I'm just checking that grams, that matches, and the density of the metal is 5.56. Now you do this in maths. So Dave's massive verruca, density is mass over volume. I've just got to divide those. So nice and simple. So the volume, V, equals the mass divided by the density. Physics we use, it's not really a P like that, we use rho for density. So I could happily have put a Dave in there instead, a D for Dave. So now it's my mass, 6.4, divided by the density, 5.56. Shove that in a calculator, 1.2. And then to get the volume, check this part. Yep, you're going to be giving it me in centimetres cubed. So that's that done. Next one, explain how the particles in solid gold are arranged and are moving differently to liquid gold. So in a solid, they're vibrated, the particles are vibrating around fixed positions. So that's their moving and that's how they're arranged. In a liquid, they're moving over each other and the crucial word is randomly. Next one, what is sublimation? So this is a change of state. And this is when we go straight from a solid to a gas or a gas to a solid. So carbon dioxide sublimes. So it's a change of state, and you could pick solid straight from a solid to a gas or straight from a gas to a solid. It misses out at the intermediate liquid phase. Next one. So now we've got specific heat capacity. So I'm going to try to teach this badly, but I'm going to try and teach this in about a couple of minutes. So the basic idea is, imagine I've got a chunk of metal and a chunk of wood, and I've got the same volume, let's say, or the same mass. Let's say I've got 1 kilogram of each. And if I was to now put 10 joules of energy into each, well, you know, so this is going to be metal, this is going to be wood. You know that if I put the same energy into each of these, this one is going to increase in temperature more than this one. Metal's a better conductor. Now, we call specific heat capacity C, okay? And what it is a measurement of how much energy do I have to put in to raise you by 1 degree C. And scientists have taken loads and loads of substances, in fact, most of the substances, and worked this out. So we just take a substance. You can imagine I've got my mystery substance here. Let's get a block of it. So you don't know what it is. I'm going to take 1 kilogram because you've got to have the same mass. And I'm now going to measure how much energy you need to go up by 1 degree C. So I just need how much energy do I need for 1 kilogram to go up by 1 degree C. That's the specific heat capacity. Now, the equation for this is the amount of thermal energy depends on the mass of the block times this constant that will work out C times the change in temperature. So we're going to see, we're going to need Q equals MC delta T, but I will be teaching this in class. So rub all of this out. And now let's go through this in terms of specific heat capacity in your full definition. So it's the amount of energy required to raise the temperature of 1 kilogram of a substance by 1 degree C. So it's 1 kilogram, 1 degree C. How much energy do I need? Okay, so that's that. So ultimately, a way to think about this is specific heat capacity. What's a nice way for me to teach it? Yeah, okay. Get a dashed line. Imagine I take an ice cube out of the freezer. So I'm going to take my ice cube out at, say, minus 15 degrees C. What will happen is, and this is 0 degrees C, is change my colour. This will start to heat up, and as it's heating up, its temperature goes up. This is my Q equals MC delta T. How much energy do I need to raise your temperature from minus 15 to 0? But then what's going to happen is this ice cube is going to start to melt. When it melts, the energy goes into breaking bonds. So here is it melting. This is what we call specific latent heat. How much energy do I need to change your state? And again, we pick 1 kilogram. Once it's fully melted, what we'll then do is we'll put heat energy in. and the temperature will go up. Q equals mc delta T. Then what's going to happen is it'll start to evaporate. So we've got, and I'm going to take all of that out. If I'm changing your temperature, I need the specific heat capacity, C. If I'm changing your state, I need specific latent heat, L. And there's two types. Fusion is if I'm melting or freezing you, and vaporization is if I'm condensing or boiling you. So that's that. So that's one way of explaining it. So now we can see then, the first one, specific latent heat, is changing your temperature. And the second one, specific heat capacity is changing your temperature, 1 kilogram by 1 degree C. And specific latent heat is how much energy do I need to change your state. And fusion is melting or freezing. So it's the amount of energy required to completely melt or freeze 1 kilogram of a substance. And then we've got some calculations to do. So we've got specific latent heat. For that one, you're going to need my quirky llama. And this is the heat energy. So sometimes it's written as E. And what's the total thermal energy? Well, I need Q equals ml. So I've just got to put that in. Now, the crucial part is we can see that's in kilograms. This is in grams. So I've got to divide you by 1,000 to get you into kilograms. And then we're away. It's a relatively simple problem. So Q equals M times L, 0.04. I've changed you into kilograms times the number that I've got there. 90,400 joules. Done. That's how much energy I need to boil 40 grams of water. And now we've got a specific heat capacity one. So if I just get this here, that's going to be Q mc delta T. So a deep fat fryer is filled with 2.4 kilograms of oil. Okay. It tells me that the heating element supplies 302 kilojoules. Okay. Calculate the predicted final temperature of the oil given its specific heat capacity is 1.9 joules per gram degree C. So I'm going to leave you alone, and then I'm going to change you to grams, so times 1,000, and I'm going to change you to joules times 1,000. So I'm leaving whatever the value is for my specific heat capacity and changing the other things to match. And it wants the final temperature. So it starts at 22 degrees C. I'm going to calculate the temperature change, delta T, and I'll circle that here, which is Q over M times C. And then I'm just going to add that to the 22 degrees at the end. So here we go. Q equals MC delta T. That'll be in your formula book. So delta T equals Q divided by M times C. Now for all my fancy unit changes, Q is 302,000 divided by 2,400 grams, because I wanted you to have the same units here, joules and grams, multiplied by 1.9. It's gone up by 66.2 degrees C. That's the change in temperature. Well, it started at 22, so I've just got to add that on. I hope that makes sense. Next question says, the actual final temperature when they did this was 62. Why is this lower than we predicted? So we're predicting 88.2. Well, why? Well, it's because we're going to lose some heat energy out of the oil. Some's going to go into the air. And it's that beautiful question of thermal energy has been dissipated into the surroundings and lost from the oil. Next one. You will be doing this practically. So describe the practical procedure to measure the specific heat capacity of water. So I'm just going to get this equation ready. So we know it's Q mc delta T. Your method should include apparatus, any measurements taken and any calculations required. So, well, that's that. It wants the specific heat capacity. So I know that that's going to C equals Q over M delta T. So what I've got to do is explain what equipment do I need to measure the heat energy? What equipment do I need to measure the mass? What equipment do I need to measure the temperature? Put it all together and then do my final calculation at the end. So to measure the energy, I'm going to use a joule meter. There are more complicated ways to do that, but just use your joule meter. So I'm going to plug a heater in, attach it to a joule meter, and it'll tell me the energy used. Mass, I need a balance. And the temperature change, I need a thermometer. And the crucial part is I want the specific heat capacity of water. So in a nutshell, here's me drawing it. Get a measuring cylinder, measure out a volume of water. Because I know 1 gram of water equals 1 centimetres cubed. If I wanted to, I could put that on a balance. So I'm now going to say I'm going to take, let's take 250 centimetres cubed of water. Next bit. Transfer that into a beaker. And we're going to have a heater over here on a mat just warming up so it gets up to temperature. I do not want to waste energy in warming up the heater beforehand. So I'm going to preheat my heater. Next part then, I'm going to put some insulation around here. I'm going to put a lid on it to prevent evaporation. And then I'm going to take the temperature at the start. So TS. I'm then going to add this, and this is connected to a joule meter. It's going to measure the joules. That's that part there. Let's change my colour. So that's that. The mass was from the measuring cylinder. So 250 centimetres cubed is 250 grams of water. That's sat in here, 250 grams. And then I'm going to put a certain amount of joules in. The crucial part is, how do I know when to stop? Well, I do not want to be boiling this water. The hotter I get this water, the more energy is going to dissipate into the surroundings. So I'm then going to see, I'm going to stop temperature end when it's gone up by about 20 degrees C. Then I'm going to stop. All right. So I now know that that's 20 degrees C. I know that that mass is 250. I'm going to read this from there and do the calculation. So that's it done pictorially. Now I'm going to just put model answer, getting rid of all of this terrible diagram. You will be doing this practically before you mock, as it's a required practical. I think it's quite a nice required practical as well. Easy-ish to understand and easy-ish to explain. Far better than that grim motor one. Okay, so use a measuring cylinder to measure out 250 centimetres cubed of water, or 250 grams of water. Add it to an insulated beaker with a lid to stop thermal energy transfer. Preheat an immersion heater connected to a joule meter. Now, when we put it into the water, we'll zero it. Use the thermometer to take an initial temperature of the water. So you can see we're always talking about the equipment we need. Heat the water by 20 degrees C and note the energy change on the joule meter. C equals, in joules per kilogram degrees C, Q divided by 0.25, because that's 0.25 kilograms, multiplied by the 20 degree temperature change. Done. That's it.